So welcome. So this is the first lecture in our Physics 2. This is the Monday-Wednesday class. And we're going to start talking about oscillatory motion. The first 4 chapters are on vibration and waves. And they're needed so that we can talk about AC theory and also light later on. So we're going to talk about what is simple harmonic motion. We'll play with it. It's almost like we've got Physics 1 skills and we're going to apply them. So, okay, let's talk about acceleration versus displacement for a simple harmonic oscillator. Let's talk about the displacement of this oscillator at any time. Let's see if we can calculate the velocity of this oscillator at any given time. Let's see if we can calculate the acceleration of this oscillator at any given time. So we're going to play with the math of it. And then we're going to start asking ourselves questions like, what physically determines the natural frequency of an oscillator? We know that a pendulum has a certain natural frequency. Well, oscillators tend to have natural frequencies. They tend to have a frequency that they prefer. Even when you bang on a table, it has a frequency which is different depending upon the shape and the size and the physical characteristics of the oscillator. And every time you hit the draw, it'll sound like the draw. It's not going to change next Thursday because it's bored. It depends on its physical properties. So what physical properties determine the natural frequency of an oscillator? And then we're going to play some more games. And we say, well, okay, if we know about acceleration and velocity and displacement in time, maybe we can talk about kinetic energy at different times. And if we know about kinetic energy, maybe we can also contrast that with potential energy. And we can add those two together and get mechanical energy. That's straight out of Physics 1. And then we can start saying, well, let's get a bit general. The problem with all this so far is that it all relies upon an idealized oscillator. We move it to the right and we let it go when our clock is 0 seconds. And we can do it perfectly from then on. Supposing you don't let it go at 0 seconds. Supposing you let it go a half a second early or a half a second late. Or supposing you don't let it go, you push it with a certain velocity. Can I do that? And it turns out, although it sounds like it would be awful, you can actually take into account a lot of those practical issues by developing this idea of a phase angle, which we'll get to. It's a very nice way of just generalizing the idealized wave equations. And then another practical thing we can talk about is damping. You know, you don't always have an oscillation which goes on forever. Sometimes energy is lost, especially through thermal energy, through friction to thermal energy, and then you lose it from the mechanical system. Oscillators, pendulums stop swinging after a while. So can we model damping? It turns out to do it mathematically, we need differential equations, and that's not a prerequisite for this course. So although you may have done differential equations, we don't. We just talk in more general terms about it. But the math is there in the book if you need it. I don't deal with it. It's so long since I've done it. And then the last thing we talk about is resonance. So that's where we're going to go in this first chapter. Later on, we'll talk about waves. This is all about oscillation. Then we're going to talk about waves. Then we're going to talk about basically sound waves because they're really important. And finally, we're going to talk about the interference of waves, be they mechanical or sound or whatever. So 4 chapters. So the picture I have in my head is of a spring mass system rather than a pendulum, because the geometry of a pendulum is actually quite sophisticated. There's angles involved and all that kind of stuff. And for introducing this idea, I'd sooner just have a mass and a spring. And because a mass on a spring, if you hang it vertically, is asymmetrical because gravity is pointing downwards, I'm going to take a frictionless table and have the spring horizontal on this frictionless table and have my oscillation go backwards and forwards like that. So it's a bit artificial, but it just means that It's a purer system. Later on, I can worry about these other things if I want to. And I'll find that mathematically, I already have what I need to do to be able to discuss these systems pretty well. So we say an object moves with simple harmonic motion. Not every oscillation is simple harmonic. Some oscillations, let's go to a bit where my pen's working. Some oscillations, if you looked at them, would go like that. And some oscillations might go like that in time. And time's going downwards, and some oscillations might go like that. And some oscillations might look very similar, but not be quite as rounded. And of those, only one of them, I would say, approximates to simple harmonic motion, and it's this guy. When you get a sine curve or a cosine curve, then you got simple harmonic motion. Simple harmonic motion occurs whenever its acceleration is proportional to this displacement from some equilibrium position and is oppositely directed. Oh my word. Lots of words. What it basically says is you get simple harmonic motion when it obeys Hooke's law. So we say the restoring force, Fr, the restoring force is equal to minus kx. What this says is that the restoring force is linearly equal to the displacement from equilibrium. That's what x is. If I double my x, I get double my restoring force. If I'm twice as far away from my equilibrium, I get twice the restoring force. If I'm 3 times farther away, I get 3 times the restoring force. Not everything follows that. Gravity doesn't follow that. Gravity doesn't follow this linear relationship with displacement, but springs do, and a lot of mechanical systems do actually. The K simply says it's constant. It's a constant proportionality. Not every spring's the same. Some springs you need you get a big restoring force for a given displacement, so K would be big. For other springs, you get a small restoring force for a given displacement, and for that for that K is a small number. So K is the stiffness of the spring. And it's measured, if you think about it, in newtons per meter. So a stiff spring might be 1,000 newtons per meter. A weak or a soft spring might be 0.5 newton per meter. It just depends on the stiffness of the spring. And then the negative sign simply means that if my displacement is in a positive sense, my restoring force is in a negative direction. And if my displacement is in a negative sense, my restoring force is in a positive direction. So if we cut this equation to pieces, it's a linear relationship between the restoring force and my displacement. My displacement is my distance from equilibrium. And it's a vector. I mean, that's a vector, and that's a vector. And it's constant for a given spring. And the force vector and the displacement vector are always in opposite directions. That's what that negative sign gives us. So whenever you get any system that obeys Hooke's law, then you get simple harmonic motion when it oscillates. And we say a block and spring combination is a simple harmonic system. Consider a block that is attached to the end of a spring. The block can slide horizontally across the smooth horizontal table. Big mistake for this first equation is people, and the book puts it down, I think, as F, not FR. People think of it as the applied force rather than the restoring force. And so this is a tip that I'd give you is, you can look at the equations casually and you'll get some understanding. But there'll be times when you make mistakes because the equations by their nature are really quite precise. And so it's really important that not only do you know what the letters are, but also precisely what the letters stand for. And I'll try and highlight when there's common misconceptions. But the most common misconception is this: is I will tell you, oh, I applied a 7 Newton force and pulled this mass 3 meters to the right. And I might ask you, what's the spring constant? Because I talked about the applied force, people tend to just assume the force is the force that I told you about. I told you about the applied force. I didn't tell you about the restoring force. This equation needs the restoring force in it. So always be careful that you know what the letters really stand for when you look at an equation. Okay? So yeah, FR is equal to minus KX, and because I'm pulling this thing at equilibrium, FR equals my applied force. Numerically, it's the opposite direction, but it's numerically equal to it. Okay, so let's take Hooke's law. Let's play with this. Does Newton's second law still apply? Yeah, I think it does. F equals ma. Just because it's a different semester doesn't mean to say that I can't apply this. So I also know that F equals ma. And so I know that this value is equal to that value. So I know that minus kx is equal to ma. So I know that a is equal to minus k over m times x, where a is a vector and x is a vector. X is my displacement. Sorry, I need to just turn my thing off. Can you see how we got an equation that I would not have been able to intuit from my conceptual understanding, but by using math, combining two equations, I derived something which gives me an insight. So I really do get the impression we're like, you know, a kid who learns to ride a bike, and that was physics 1, and now we're riding it over hillsides, and now we're riding it on a track, and now we're riding it through streams to see how well it works. We've learned some skills in physics 1. Now we're going to try and apply that mechanics to oscillating systems. So we derive this. Why did we derive it? For the fun of it as much as anything else. It's like, I don't remember this equation. I know that equation. I know that equation. I can get that equation anytime I like. Okay? But I can ask you about that relationship. Okay? So. Simple harmonic system. Is acceleration constant for different displacements? Let's just recall that equation. We said A is equal to minus k over m times x. Is that right? Actually, let's stop for a minute before we get there. Always ask yourself, does this make sense? If I have a big mass, will my mechanical system get more sluggish or more agile? Big mass. That'd be more sluggish, isn't it? Mass increases your inertia. If I have more sluggishness, what can you tell me about the acceleration of my motion? If it's sluggish. Yeah, it's a lower acceleration. Big trucks cannot accelerate as fast as a little moped. Watch them in traffic lights. Little moped takes off. Big truck gets left behind. A little moped is... So that makes sense. Mass should be on the bottom. If I have a stiff spring versus a slack, I'd expect a stiff spring to oscillate quite quickly. That's a lot of acceleration. It's a varying acceleration. It's a lot of acceleration. And then, so now I look at this. So that makes sense. Bigger displacement means that I stretched my string further. That's bigger forces, bigger acceleration. So x should be on top. So now let's think about this question. In a simple harmonic system, acceleration is constant for different displacement. Is A constant when I change x? No, my spring's constant and my mass is constant. I can't be changing those in the middle of my expression because then I don't know anything. So yeah, so this is no. It's not constant. What about this? What kind of relationship links acceleration with displacement? So what kind of relationship is it? Is it linear? Is it inverse? Is it parabolic? What is it? Look at your equation. A is equal to minus k over m times x. You're not changing k and you're not changing m, so that's a constant. So A is equal to constant x plus 0. That's a straight line. That's linear. Try and get to the stage. I'm your teacher. I'm writing the test. If I think it's important, at least for this course, it's important. I'm a visual thinker. If you're not a visual thinker, you've been tested by a visual thinker. What I think of as straightforward, you might struggle with. You got to practice visual thinking. So this is an important skill. Can you look at an equation and figure out what the graph is like? Is it linear? Is it inverse? Is it parabolic? With a bit of practice, it gets easier and easier. That's linear. In simple harmonic system, is acceleration constant for different times? A is equal to minus k over m times x. I'm doing A and T. Yeah. Now that's not in my equation, but think about it. Visualize it. I move this to one side, there's an x, and then as I change x, my A changes. Agreed? Yes. My A changes whenever I change my x. Do I do that instantly or do I do that over a period of time? So really, there's my time. I said that my acceleration is different for different x's, yeah? I did that up there. My acceleration is different for different x's, yeah? And I have different x's at different times, yeah? So my acceleration is not constant in time. It's got to change. If my position changes in time, if my acceleration changes with position, and my position changes in time, then my acceleration must change in time. Yeah? So even though it wasn't part of the equation, by visualizing, it's not just math. You've got to visualize and say, oh yeah, well, position depends upon time, and time depends upon position. So even though it's not in my equation, I can figure out what's going on. Okay? And that's just thinking a bit more deeply about what the equation means. So, next bit. I'd like to mathematically describe this oscillation, and it's incredibly hard. And then somebody, I'll leave it, I've only got a few minutes. If you look online, I sometimes have pictures, I sometimes have videos of this. I'll see if I've got a video up of it. Somebody had this really smart idea where they looked at a mass oscillating backwards and forwards, and they had a turntable with a can on it. And sure enough, what they found was that the position of the can and the position of the oscillator kept track with each other. So what that means is that as this thing goes, they're in line with each other. 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 So this is going backwards and forwards and backwards, and this is going round and round and round. So uniform circular motion. If I take the x component of uniform circular motion, I can describe simple harmonic motion perfectly. Perfectly. Okay. Well, how can I use uniform circular motion? So Here's my uniform circular motion. Here's my can going round in a circle. And here's my thing that's oscillating backwards and forwards. And it's the x component of these two. Why is it the x component? Because I'm cunningly moving my oscillator to the right along my x-axis and letting it go. I'm deciding it's the x component, but it is the x component for these diagrams. I started off here, and my actual oscillator moved that like that, and my circular motion moved like that. Now, my displacement is the x component of this triangle for the circular motion. My velocity for the oscillator is the x component of this velocity for the circular motion. My oscillator's acceleration is the x component of the centripetal acceleration. I've got to do components. If you manage to get through Physics 1 without mastering components, it's coming back to bite you again. It's like, they never go away. So we say uniform circular motion is directly related to simple harmonic motion. The angle changes with time, so it's best to express it. So as this thing goes backwards and forwards, time is changing. I suppose traditionally I like to call this theta. In radians, doesn't matter. But theta must depend upon time. It's the angular velocity times radians is equal to radians per second times seconds. Yeah. So by all means feel uncomfortable about omega t, but by tomorrow get comfortable with it because it's just an expression. The angle changes in time. Okay, it changes by the angular speed times time. We're going to call it angular frequency because we're dealing with oscillations. Omega is angular frequency now. An object displays uniform circular motion. It has an angular velocity of 6 radians per second. How long does it take to revolve through 30 radians? Okay, so let's have a look. My omega is equal to my delta x, or delta theta really, over delta t. So my delta t is equal to my delta theta over my omega. This equals 30 radians divided by 6 seconds, which is 6 radians per second, which is 5 seconds. Now, I don't know about you, but I've been doing this for like 20 years, and I'm always a little bit uncomfortable at this point because there are terms that we don't use very often. And so the fear is you'll get them backwards. Let me express this in different ways. A car has a velocity of 6 miles per hour. How long does it take to go 30 miles? 5 hours. Yeah? It's the same question, isn't it? I'm just using miles rather than radians and miles per hour rather than radians per second. It's the same problem. You're just unfamiliar with it. It's not that it's mathematically hard. It can't get any easier than that. But it's unfamiliar. So part of the battle, especially in Physics 2 that you face, is that there's twice as many terms are going to be coming down, and you've not heard them before. So a fair bit of what you've got to do is actually bibliography keeping, making sure you know the terms. And just dealing with, spending enough time playing with this guy so that by tomorrow it's not such a alien thing. when I was a student, I spent my time trying to solve the harder problems and would eventually struggle through, exhausted like at the end of a marathon. And in a way, I would have been much better off taking that energy and getting really good at running the first 15 miles. Because it wasn't a test on can you finish the marathon. It was how well can you run. So to some extent, by sweating the simpler detail, it makes the harder stuff much more accessible. And so you're much more efficient. I suspect if I'd, in marathon terms, I've never run a marathon, I suspect that if a runner tried to run a marathon one day and then tried to run a marathon the second day and tried to run a marathon the third day, or maybe 1 week and then another week and then another week, they would not do as well as if they tried to run 3 miles every day, 3 miles the first day, 6 miles the second day, 9 miles the third day. There is training, building up on things. And if you only try and do the difficult things and you don't train yourself in the simple things, I think you'll make simple mistakes. So spend some time on this. An object displays uniform circular motion. It has an angular velocity, omega, is equal to 4 radians per second. How long does it take to revolve through theta, delta theta? How long does it take to revolve through 120 radians? Oh, how long delta t? Oh, I get it. Omega is equal to delta theta over delta t. So delta t equals delta theta over omega, which equals, let's have a look, 120 over 4, which equals 30 seconds. Piece of cake. And where did I get this omega? Well, I know that omega is like v, and I know that delta theta is like delta x. I know delta t. We did that at the beginning of Physics 1. So I'm using analogy to go from linear to angular. And then I'm just letting the math go through. It's not hard. And it's not a test on your intelligence. It's just time on task. That's all it is, time on task. We're out of time. So let me prime you a little bit. So all we do now is we have a diagram. And I write an expression for the horizontal component of displacement. I write an expression for a horizontal component of velocity. I write an expression for the horizontal component of acceleration. And it falls out. We'll do this next time. Try and get ahead of me. Try and come in next time and know this bit cold. And just from now on, try and be ahead of me.